Industry 4.0 is expected to add trillions of dollars in value through enhanced productivity and optimization over the next 10 years. The chasm between the Industry 4.0 haves and have nots is growing at an unprecedented pace. The question is no longer whether or not one should adopt it. The question is whether one would survive if one does not. This presentation aims to give an overview of Industry 4.0, a rapidly developing form of intelligent manufacturing processes assisted by digital technologies, artificial intelligence, and data analytics. Building on this overview, a curriculum for Industry 4.0 has been suggested for students of engineering. The term Industry 4.0 was coined by the German government as part of a strategy to promote the advanced technology enabled manufacturing. It was introduced at the Hanover Fair in 2011. Industry 4.0 has been adopted by most leading industrialized economies in the world. The central idea of Industry 4.0 is large scale optimization of industrial operations across a wide range of parameters using a bouquet of technologies that form part of the fourth industrial revolution, a term popularized by Klaus Schwab, founder and executive chairman of the World Economic Forum. Introduction of Industry 4.0 in engineering curriculum is well aligned with the National Education Policy 2020. Let us examine some of the key policy guidelines. Academic autonomy and modular programming. Academic autonomy allows institutions to introduce modular programs that can be updated as technology advances. Multidisciplinary and holistic education. Industry 4.0 is inherently multidisciplinary, combining digital technologies, data science, artificial intelligence, robotics, and communication technology. National Educational Technology Forum. The NETF supports appropriate integration of technology, providing formal policy basis for introducing advanced digital manufacturing and IIoT concepts into the engineering syllabus. Curriculum redesign for emerging technologies. This recommends development of instructional material and video films for emerging technologies. Industry academia collaboration on skilling. This fosters collaboration with industry leaders through programs grounded in real world application. The National Institute of Technical Teachers Training at Bhopal has created the Center of Excellence for Industry 4.0 and digitization. The center has been developed in collaboration with Siemens Industry Software and 3D Engineering Automation. It aligns with NEP 2020. The Center of Excellence is a vital node for Skill India mission. The 11 pillars of the COE are robotics and mechatronics, Internet of Things, additive manufacturing, digital manufacturing, product design and validation, simulation and optimization, CNC controller, and process automation. The NITTR Bhopal Center of Excellence is a cornerstone of the Institute's Vision Plan 2036, aiming to make Bhopal into a major technical training hub for the entire Asian region. The key technologies used in Industry 4.0 include cyber physical systems, industrial Internet of Things, communication networks, closed loop feedback systems, cloud manufacturing, manufacturing analytics, artificial intelligence, virtual reality, augmented reality, digital twins, industrial robotics, and additive manufacturing. Each of these technologies will be explained in the following section. Cyber physical systems are primarily a system of sensors and actuators. The sensors are devices embedded in industrial systems and are used to monitor physical parameters such as temperature, flow, proximity, vibration, pressure, emissions, and sound. Actuators are the mechanical devices that are operated by controllers to take corrective action, leading to process optimization. The Industrial Internet of Things is the technology that connects the physical systems using cables, wireless communication systems, and the Internet. The connected system is referred to as the Industrial Internet of Things. The IIoT connects the sensors and actuators with the controlling systems, such as the programmable logic controllers, the supervised control and data acquisition systems, the human machine interfaces, and the edge computing environment. Data is processed by the controllers and the system is optimized using artificial intelligence and machine learning algorithms. The feedback given to actuators provides the necessary corrective action. The process generates massive amounts of data, rightly referred to as big data. The facility that is used to store this data and offer controlled access is known as the cloud. Data requiring real time response is maintained closer to the operation and is referred to as edge computing. The cloud environment hosts data concerned with design, development, infrastructure, processes, and manufacturing. Engineers located in different parts of the world can collaborate to design and develop advanced industrial products. The cloud environment can be used for analytics and business intelligence. The cloud services can be rented on a scalable basis. This enables small players to avail of cloud services without making the investments in the facility. The heart of intelligent manufacturing is data analytics. It comprises of descriptive analytics. It explains what is happening. Diagnostic analytics. It explains why it is happening. Predictive analytics. It tells you what can be expected to happen. And prescriptive analytics. It tells you what needs to be done to achieve the desired results. Virtual reality is a simulation of a physical three-dimensional world. Users can interact and navigate through the digital space as though they are physically present in it and as though the space were real. Augmented reality. Augmented reality assists manufacturing and maintenance teams by overlaying real time digital instructions, 3D repair guides, and performance data directly into their physical view of the machinery. A digital twin is a dynamic virtual replica of a physical asset or system. It uses real time data to simulate, predict, and optimize its performance and carry out experimentation without disturbing the physical system. Digital twins can be created at the level of a component, an asset like an aircraft engine, a system like an assembly line, a process including material acquisition, manufacturing, and supply chain, and a product through its entire life cycle from design to disposal. Industrial robots are widely used in Industry 4.0 to carry out dull, difficult, and dangerous operations known as the 3Ds of automation. Industrial robots are commonly used for robotic welding, assembly pick and place, packaging and palletizing, inspection and quality control, CNC machining, and material handling and logistics. Collaborative robot or cobot is a specialized robot designed with integrated safety sensors to work alongside humans in a shared workspace. It augments human skills by handling repetitive or strenuous tasks, complementing the ability of the human operator to perform complex tasks requiring judgment and dexterity. A typical example of a cobot is the exoskeleton. The exoskeleton is a wearable mobile machine powered by a system of electric motors, pneumatics, levers, or hydraulics that enhances the human operator's physical strength, allowing for limb movement with increased strength and endurance. Robots are automated using advanced algorithms. Some commonly used algorithms are object detection, localization and mapping, and motion planning and control. Robotic design includes advanced sensors used for automation. Some critically important sensors are force and torque sensors and proximity sensors. Robots perform tasks using grippers and end of arm tooling. Choice of grippers and UAT is critical to robotic design. Industry 4.0, with its highly enhanced focus on optimization and automation, seems to leave the human operator out of reckoning. Industry 5.0 tries to humanize the Industry 4.0 centric operations by stressing upon enhanced autonomy, empowering people, customization and flexibility, sustainability and ecological responsibility, human centricity and ethics, and continuous learning. The technologies explained here are used wherever complex machinery and process equipment are deployed on a large scale. Operations need to be optimized by the extensive application of digital technologies, manufacturing analytics, and artificial intelligence. Effectively, every domain of engineering requires a good understanding of Industry 4.0 technologies, though the level and depth of coverage may vary across streams. The key constituents of the proposed Industry 4.0 curriculum will include the following: the fourth industrial revolution, key technologies of Industry 4.0, industrial automation, mechatronics and robotics, Industry 5.0, artificial intelligence in manufacturing, and Industry 4.0 implementation roadmap. The coverage of the fourth industrial revolution will include drivers of the fourth industrial revolution and combining the digital, physical, and biological worlds. The key technologies of Industry 4.0 will include cyber physical systems, industrial Internet of Things, artificial intelligence, big data analytics, cloud computing, blockchain, additive manufacturing, virtual reality, augmented reality, digital twins, predictive maintenance, additive manufacturing, control systems architecture, security challenges in control systems, operations technology and information technology, cyber security for industrial control systems, factors driving the development of Industry 4.0, and lean and agile manufacturing in the digital age. Industrial automation, mechatronics, and robots will include application of industrial robotics, robotic control, robotic sensor technology, end of arm tooling, collaborative robots, and emerging trends in industrial robotics. The key principles of Industry 5.0 will include enhanced autonomy, empowering people, customization and flexibility, sustainability and ecological responsibility, human centricity and ethics, and continuous learning. Artificial intelligence in manufacturing will cover data driven decision making and AI in operations, AI driven process optimization, augmented operators, and the use of ERP systems. And finally, Industry 4.0 implementation roadmap will include smart factories from concept to reality, the smart manufacturing journey, the layered structure of a smart factory, maturity stages of the smart manufacturing journey. We have reached the end of this presentation. I hope it has helped you to gain an understanding of Industry 4.0 and the constituents of the proposed curriculum. Thank you for your attention.